This is a video for OCR Pure Core Mathematics, Sequences and Series 2, Maclaurin Series, 2.1, Polynomial Approximations. In this section, we'll be approximating functions by using polynomials of this form. So there's our polynomial, and we've got ascending powers of x, whole powers of x, and we've got coefficients for each part a, b, c, d, and so on. And those coefficients are all real numbers. Now, polynomials are relatively easy to use. We can differentiate them easily and so on, and therefore we often use them to approximate more complex functions. Furthermore, if the coefficients are chosen correctly, the polynomial gets ever closer to the function as the powers of x increase. So let's say we want to approximate the function fx is equal to e to the x. Well, one of the things we could do is we could fit a linear polynomial, so px is equal to a plus bx. And if we want to get as good a fit as possible at x equals 0, we try and make the value of p equal to the value of f and the gradient of p equal to the gradient of f at that point. So let's have a look at what we've got. If px is a plus bx, then p dash x, and I'm using dash as the derivative with respect to x. It's a much tidier notation in this situation, so p dash x will just be equal to b, and if we differentiate e to the x, we just get e to the x. So if we look at p0, p0 is just equal to a, and p dash 0 is just equal to b. And f0 is equal to 1, e to the 0 is just 1, and f dash 0 is also equal to 1. So this would suggest that a equals 1 and b equals 1, which means I want my polynomial to be 1 plus x. So there's my polynomial, and here's a plot. Green curve is e to the x, and the red line is 1 plus x. And whilst the approximation is actually quite good around x equals 0, you can see that as soon as you get very far away, and on this plot you really aren't very far away, they deviate quite significantly. So how can we improve that? Well, we could fit a quadratic, so we could use px is a plus bx plus cx squared, and then do the same as before. So we want to make the second derivatives of p and f equal at x equals 0. Just double check those. The first derivative of px then is going to be b plus 2cx, and the second derivative will be 2c. And we know that the second derivative of our function, it's just differentiating e to the x again, will be e to the x. And so p double dash 0 is 2c, f double dash 0 is just 1, so c equals a half. And there's a plot of the two functions. There's 1 plus x squared over 2, and there's e to the x, and the range of values for which this is a fairly good approximation is slightly larger, but still restricted to very close to 0. However, let's have a look at a dynamic plot of that and allow me to increase the order of the polynomial that I'm using for the approximation. So here's the quadratic fitted. If I push that up to a cubic, so order 3, it's a better approximation over a larger range of x, and as I push on up, you can see that actually as x gets above 1 here, this is not a bad approximation by the looks of it on the graph. And if I push up to something like 9, then this is pretty much indistinguishable. And indeed, if I zoom out on this, you can see that I'm still hard pressed to see any of the green line up here. Obviously the tail, the left-hand end of this, will just get better as I increase the order of the polynomial that I'm using to approximate. Now we can apply this approach to a wide range of functions, not just e to the x, provided that the function and its derivatives can be evaluated at x equals 0. And here's a polynomial of order 7 fitted to sine x, and the next video in this sequence is going to look at Maclaurin's series, which is just a generalized form of this method. The next video in this sequence is 2.2, the general Maclaurin series.